Hi, everyone. I realize my talk is kind of in the wrong session. It's my own fault because the one time I decided to book my travel well in advance, these schedule changes. So I apologize. It should probably be in the next session after Sarah Martel's. The one advantage is, of course, that I can use my alternative Gala logo with the outstretched wings grasping the galaxy in its talons. So hierarchical assembly of galaxies is pretty much, it is the paradigm right now. There's a lovely illustration from 2009 by Marie Martig. And so we know that the Milky Way, other galaxies have assembled hierarchically. Little things come together to build bigger things. What can we use to trace this assembly history? So I'm going to talk about chemistry meaning elemental abundances as a way to do this. And I'm going to be presenting results both from Gala, which you're probably familiar with, and the S5 collaboration, which you may not be. So what observational evidence do we have for accretion events in the Milky Way, that is? Sorry, I qualify that. In the halo, we see spatially coherent streams. So you see here in the rainbow on the, sorry, just get the cursor over there. You see a Sagittarius stream, which is bifurcated. This is a large Magellanic Cloud. This is a combination of Sloan and DS data. But you see streams throughout the halo, and the more you look, the more streams you see. So there'll be lots more, I'm sure, with LSST data. Within the galaxy itself, in the disk and bulge, we tend to find accretion events or find evidence of accretion events through kinematics, the motions of stars, and also through their abundance patterns. One example of this, a very large example of this, is the so-called Gaia sausage Enceladus. Yes, it's a very strange name if you haven't heard it before. Amina Helmi called it Gaia Enceladus. Vasily Belokorov referred to it as sausage-like. If you look at this, calling it the sausage, just again, this is in kinematic space. But this was a significant merger that we think happened, I believe, 8 or 10 gigayears ago. And we can see the evidence of it within the galaxy itself. Just as a warning, this will be talking about chemical abundances. Gratuitous furry animal picture. So periodic table, this is a lovely picture produced by Chiaki Kobayashi, showing you where all the elements come from, or where we believe all the elements come from. And it ranges from the Big Bang, you can see in black there, low mass stars in green, exploding massive stars in purple, orange for exploding white dwarfs, that would be type 1a supernovae, and then merging stars in the mauve. And so as you can see, that often there are multiple channels for producing a given element, but one of the things we can do by looking at different elements and looking at their ratios is try to figure out what was the environment like, what sort of material did the star form out of, and hence, where did it form, under what conditions did it form. So this is a lovely animation from Sven Buder. Basically, an example of this would be lithium. Lithium, for the most part, formed through Big Bang nucleosynthesis. We've got, these figures are not showing up great. Hold on. There we go. Sorry, jumped the gun. Lithium, this is a plot of lithium from Gala data. Sodium is from a mixture of different mechanisms, both exploding massive stars and also asymptotic giant branch stars. Magnesium, again, exploding massive stars, so type 2 supernovae, and also asymptotic giant branch stars. And again, these are plots of data from the Gala survey. If you're not aware, the Gala survey is now up to 800, 900,000 stars. Yeah. Manganese, a little more complicated, type 1a supernovae, but trace amounts from other things. Barium, primarily asymptotic giant branch stars, and europium, yes, that is an element. Again, massive stars, asymptotic giant branch stars. But this is showing kind of their ratios compared to iron versus iron to H. So it's looking at kind of their evolution. Sorry. So basically, the idea is that you look at the relative amounts of different abundances to figure out what was going on when the star formed. Because for the most part, the elemental abundances in stars stay the same from birth to death, or at least close to death. So you can think of them as, in a way, as essentially stellar DNA. All right, some very gross characteristics, gross in the sense of like general, broad, not in the sense of disgusting, characteristics of dwarf galaxy stars. So above you see sort of in the upper panel, you see sort of a theoretical model. Lower you see actual real data. So the idea is that you have, as a galaxy enriches and you go to higher and higher iron to hydrogen, so higher iron abundance, the alpha elements to iron, alpha elements primarily generated in type 2 supernovae, this relationship evolves. And so you have, in this upper panel, you have things that form in situ, typically where there's a lot of type 2 supernovae. As the type 1a supernovae kick in after a delay of, say, 1 or 2 gigayears, then this ratio of alpha elements to iron starts to drop down. So, you know, if you're looking at the Milky Way, this would be kind of like the thick disk. This would be kind of like the thin disk. Now, accreted stars typically come from smaller systems like dwarf galaxies. In dwarf galaxies, we tend not to have such high alpha enrichment. And so you see something like this real world data plot. These are thick disk stars, these are thin disk stars. And then these squares and stars are actually from low mass dwarf galaxies that we've observed outside the Milky Way. One other note, dwarf galaxies do tend to show a range in Fe on H. So for example, you can see it goes from, in this case, -3 to 0 for the squares. Globular clusters typically show, well, you could call them strange because we don't know exactly why, but they tend to show elemental abundance anticorrelations. So in this case is the well known now sodium to oxygen anticorrelation. If it's got high oxygen, it's got low sodium, and vice versa. We don't really know why. People have ideas, but I wouldn't say that it's a solved problem. And one other thing about globular clusters is that they typically don't show a significant range in Fe on H. There are a few exceptions, but you can count them on the fingers of one hand. All right, so what can we do with Galah data? Well, one example was linking stars to their probable progenitor. So a stream was identified by Ibada et al. Using Gaia DR2 data, so basically based on the kinematics, and was potentially linked to Omega Cen. Jeffrey Simpson, who used to be one of us, and has now moved on his transition to the next plane of existence, i.e. outside of astronomy, looked in Galan to see if we had any stars from this Fimbulthal stream, and found that we did, at least based on the kinematics. And it turns out that some of them at least have abundances that are consistent with being from Omega Cen, which is kind of cool because it's like, you know, there's the idea, well, it could be Omega Cen, but these abundance patterns, Omega Cen has kind of weird abundance patterns. These stars seem to fit it. Another example would be trying to differentiate between accreted and in situ stars. In situ meaning that they formed in the galaxy, accreted meaning they formed out there and came in. You know, they came from outer space. So there was a prograde stellar stream in the solar vicinity, so near us, identified by Nesib et al. And this was in Nature Astronomy. So, sorry, like ding, 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 ding. For young people out there, something appears in Nature, it's either completely amazing and completely correct, or there's a good chance that some of it might not be just right. Sorry, personal, editorial there. In any case, they used data from follow-on from the RAVE survey to conclude that it was the remnant of an accreted dwarf galaxy. So they said it was a dwarf galaxy. We looked at it using Galah data and some other data, and we found that, so Nix, this apparent dwarf galaxy, as in the red dots, and we found that it seemed to be consistent with thick disk stars. In other words, just galactic stars in terms of abundances. If you compare it to the Gaia Enceladus sausage, Gaia sausage Enceladus in black here, it doesn't really overlap much at all. And then comparing it to thick disk, comparing it to Gaia Enceladus sausage, comparing it to the Sagittarius dwarf, comparing it to the Large Magellanic Cloud, you can see these red dots seem to overlap with the blue, the thick disk, but not with any of the other dwarf galaxies. So we decided it's probably just galactic substructure. I mean, it could have been galactic substructure induced by an interaction with a dwarf galaxy, but the stars themselves don't look like they came from out there. They look like they were born here. Sven Buder, I mentioned earlier, did a study looking at combining both kinematic and abundance data, kinematic largely, well, both from Galan and also from Gaia, and abundance data in Gaussian mixture models to try to find what combination of different elements is most likely to indicate that something formed out there as opposed to formed in the Milky Way. And what he actually found was that, at least with Galan data, a good combination was comparing the ratio of magnesium to manganese to that for sodium to iron. So this thing that he dubbed the avocado is basically most of the stars in our galaxy. And these are stars from the Gaia sausage Enceladus, Gaia Enceladus sausage. And you can see that they are chemically distinct. They're also obviously kinematically distinct as well. All right, I'm running out of time, so I'll try to speed up a bit. What about the halo? So Galan is primarily looking in the disk nearby, say the closest, say 2 kiloparsecs of the Milky Way. So we launched this S5 survey using the AAT and Aeomega as opposed to Hermes in 2018, and we've been observing since then. And we're observing stellar streams in the halo of the Milky Way, initially identified from dark energy survey data, now identified, now we're also expanding into streams identified in Gaia. And in Lee et al., we published the orbital and chemical properties of 12 halo streams. So just to focus on a couple of aspects of this, what are these streams in the halo? What are their progenitors? What did they form out of? What got ripped apart? What has our galaxy been eating? So as it turned out, we looked at 12 galaxies. About half of them look like they're globular clusters. We think they're globular clusters because they have small metallicity dispersions and they have small velocity dispersions. Dwarf galaxies tend to have higher in both. A freaky thing for the simulators out there, out of a sample of 12, the vast majority of them appear to have prograde orbits. If you look at an example simulation from FIRE, we would expect it to be essentially not have any preference for prograde or retrograde. So that's kind of a weird feature. Just to wrap up, we're hiring. So we'll be advertising 2 postdocs in the next couple of months. One of the positions will be at Macquarie, one will be at the University of Sydney. Please stay tuned if you're interested. And I will stop with this summary. Basically, stellar abundances are like stellar DNA, and they tell us about the conditions where stars formed. And so we're looking at it both within the distant bulge of the Milky Way with Galan. We're looking at the halo with S5, and chemistry is a key tool for disentangling the Milky Way's accretion history.